And good afternoon, everybody. Bob DeVance, K5CRX for the McKinney Amateur Radio Club. We're ready tonight to tackle the final class of our general license prep class that we've been doing. This will be session number 6 of all of that. We did do one makeup session this previous Saturday to kind of catch up a little bit, and then decided that we would add the digital operating section because there are quite a few questions about that, some of which may not be very obvious, shall we say. So we're going to go over that tonight and cover that just a little bit. Let me share my screen with you and I'll show you the plan for tonight. Okay, that one. Okay, so again, there's my email address and my phone number if you should have occasion to get a hold of me, of course. And then the general layout is that. And I've got to move a bar just a moment. Okay, so we've covered all those things down to the very bottom, to the digital operating, which I misspelled. But anyway, digital operating has about 48 questions in this particular presentation, and a good discussion of some of the other things. So I think it'll be a good discussion all the way around to talk about digital operating principles and procedures. This is, to me at least, new in the general test. When I took the general test quite a few years ago, digital had not made its really its intro at that point. And so we didn't really have any questions about that. So this is quite a change, but it's good because we do a lot of things in the digital world with our radios. So with that, that's where we're going with it tonight. So hold on just for a little while and we will be coming back in just pretty quick. Let me stop the share. And we'll be joining the rest of the class here just momentarily. Record to this computer. Okay, we're now recording. Good evening, gang. Thank you for putting up with me there for a minute while I was getting synced up with all the good stuff. And hopefully my screen is now shared and you can see me okay. Is that a good guess?
Yes.
Okay, then I'm going to hide my floating panel here so I don't see it and move that over a little bit so I don't see you guys. And here we go. If my machine wants to work and it may not want to. There we go. Okay, we're still cranking. By the way, just an FYI, I think I mentioned this on Saturday. I did order the extra manuals. ARRL had a weekend special going here this weekend, some reduced prices and free shipping. And so I ordered up the extra manuals. So I hope we'll be able to do that when the time comes to do that. Okay, digital operating. Here we go. Let me talk a little bit about the first slide. It's kind of interesting they picked this particular one to go, but that's okay. As I've said before, the Wes does it a little bit differently than the ARRL's layout. He tends to group things by subject, in this case, digital operating, and he pulls questions in from several different places that relate to digital, as opposed to the ARRL, which goes more by the questions themselves and just takes the questions in sequence. So we're kind of jumping in the middle of this one. The Baudot code is an old technique of sending stuff. Was primarily popular in the teletype days when we sent stuff by teletype. It used a 5-bit code with a start and a stop bit. So it was a digital code. Being that it had 5 bits, that's 2 to the 8th power, or 32 characters that it could represent natively. Because of it did that, its default mode was to operate in all capital letters. So when you got something that came in on teletype through the radio and it was in all caps, nobody was yelling at you. That was just the convention. And if you wanted to mix it up, you could change character sets. There was a code you could send it, change character sets, and then you could do numbers and punctuation and some lowercase stuff with that. But generally speaking, the key to that particular question they're going to ask is that Baudot is a 5-bit code with a start bit and a stop bit. And we'll see that one come to play a little bit later on. Dealing with RTTY, or radio teletype communications, this was one of the earliest forms of digital for amateurs, unless you consider CW, of course, digital, which some people do. But at any rate, this was one of the early attempts to send data back and forth. The RTTY uses a 170 hertz shift. It basically uses 2 tones, and it shifts back and forth between the 2 tones. I don't remember exactly. I believe it's 21, 25, and whatever 170 way down from that that is, was 19 something. I believe 2125 is the top frequency. It's called frequency shift keying. In fact, it's not the traditional frequency shift. You know, we talked about frequency shift earlier when we were actually shifting the carrier frequency. And on this, we're not shifting the carrier frequency, we're shifting the audio frequencies that ride on top of the sideband carrier. So when we say we're doing frequency shifts, that's what we're talking about, just shifting the audio tones. And we're using the two tones for RTTY radio teletype. 170 hertz will stick out like a sore thumb when you see the question. Okay, FSK, frequency shift keying signals, can be called high or low or 1 and 0 in the digital world. For this particular purpose, we use the terms mark and space instead. And again, that comes back from the old teletype world. Mark is a 1, and space is a 0. On the landlines where teletypes were connected together, the old teletype would be sitting there just going chunky, 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 doing spaces. It wasn't receiving anything. It was just marking time, literally. I shouldn't say marking. That's confusing. It was spacing out over the time when nothing was coming in. And then when the data would start to come in, then the thing would take off and start typing for you and the stuff would come out. But we use mark and space in the RTTY world. Mark is a 1, a space is a 0. Okay, audio frequency shift keying is what we use on radio teletype, RTTY. Audio frequency meaning that we have those two audio frequencies and we shift back and forth between those two frequencies. One of the peculiarities for radio teletype is it always uses the lower sideband. Doesn't matter which frequency you're on. You know, normally we use LSB for 40 meters and down, and we use upper sideband for everything higher than that. But for a radio teletype, everything is done lower sideband. And there's a couple of questions that will come up later that pertain to that as far as making some corrections if you wind up on the wrong sideband, or if the sender perhaps might be sending on the wrong sideband, which of course is always a possibility. Audio frequency shift keying just means we're using the two audio tones and we're shifting back and forth between those two tones. Okay, frequency shift keying used by a lot of different modes. The one we're talking about here, of course, is RTTY, radio teletype. When computers came into the world with their sound cards, it opened up a whole new bucket of worms. I mean, it opened up a whole new world of opportunities. That's what I meant to say, because the sound cards really can be programmed and tweaked and tinkered with and do all kinds of stuff, including picking up signals that we can't actually hear with our ears. They can actually pick that up, separate it out, process it digitally, and retrieve data from something we can't even hear with our ears. So that was a great step forward. The audio sound card actually creates the audio frequency shift keying converted to the true FSK in a properly aligned transmitter using the mark and space. And this is where I mentioned if somebody gets it backward. If we reverse the mark and space audio tones, the same effect is having the single sideband transmitter on the wrong sideband. So if you're trying to receive teletype, you can hear it, you know, there's something there, but it's not coming through. One of the quick ways to flip is just to flip your mode to upper sideband and see if it suddenly pops in. If so, then you know the other person was sending on the wrong sideband. And if that doesn't do it, then there's something else crazy that's going wrong with all of that. Okay. Make sure you're on the right band at the right rate. The radio teletype standard is 45 baud. The word baud is an old French term. It equates more or less to characters per minute. So it's not 45 baud is pretty slow. It's not running really fast out there. And then that's by design. If we speed it up a lot, then we have to have a lot more bandwidth. And these modes are very efficient. They don't use a lot of bandwidth. That's why they can run so slowly. Okay, a lot of things come and go to govern how we operate with these things. There's some conventions. For example, like we said, the upper and lower sidebands. We use the lower sideband for teletype, upper sideband for everything else. That's just a convention. It's not a rule, but we generally go with whatever is the convention, no matter what we would normally do otherwise. We follow the convention and don't argue with what people are doing. I and Q, we talked about this some time back. We were talking at that point. We were talking about modulators and demodulators, where we had an I or an input signal going into a circuit, and a Q signal. Anytime you see the letter Q in this kind of a context, it generally means quadrature or quad or 90 degrees related. Be related somehow to 90, or twice 90 or 390 degrees in phase. So an I signal is the original signal. The Q signal is at least a 90-degree out of phase version of the same input signal. So I and Q, you can determine the precise phase angle of the signals that they've been shifted by 90 degrees, and you can play all kinds of games with it. The key is all types of modulation can be created with the appropriate processing. That's really all that's saying there. We can do our electronic processing, and we can pretty much do anything we want to with that signal. And then the sound cards we're using today are detailed enough and have enough power within them, and our computers have enough power to process it, that we can make those things sing and dance if we want to. All types of modulation can be created with the right kind of processing, dealing with input and phase shifted signals. PSK31 was the granddaddy, right? It was right after teletype, first popular sound card digital mode. And of course, a lot of things came on now. FT8, of course, is the big bird right now. It didn't require an elaborate setup or a whole lot of equipment to do that in order to use the computer's sound card. Generally just had a little interface box, would take the sound out of the radio, run it through this interface box into the computer sound card's input, and the output from the computer would go through the same box, get processed a little bit, and sent into the radio mic connection. And then there would be a signal set up so that when you wanted to key the transmitter, it would send a keying signal to the transmitter, and it would transmit when it was told to do so. So it's relatively simple. You could actually do a completely passive box for that with no amplifying agents, no active agents, no transistors or anything like that in it, all just passive components. The chief being two little transformers. You would use two one-to-one audio transformers in order to isolate the inputs and the outputs to the sound card from the radio. And that prohibits a ground loop, which causes a loud hum. It just isolates one from the other and then eliminates a lot of problems. It's a passive device. And then generally they would be a potentiometer, a pot, a volume control adjustment, whatever you want to call it, for each of those. So you could adjust the level of the sound from the radio. You could adjust the level of the sound coming from the computer back to the radio. So if you haven't played around with the digital modes, little thing to note, place to find activity is 14.070 megahertz and 14.100 megahertz. Those are two of the hot digital places. And since they're both in the 20-meter band, and the 20-meter band is the nearest we have to an around-the-clock band, you can generally find activity on 20 meters any time of the day or night. I think that's why we're saying go to 1407 or 14100. 1407 is definitely PSK. 14100 will have some of that as well. And then they go up just a little bit from that, we'll see FT8. But the answer to the question here is playing with the digital modes. Look for activity at 14070 and 14100. Upper sideband, unless you're doing teletype, which is a different set of frequencies. When radio teletype, it was king back then. Only capital letters were sent, as we said before. It looked like everybody was yelling. They really weren't. That's just the way it was set up. PSK 31 has the entire character set available, but with a price. If you're yelling in PSK 31, if you try not to yell, is what they really meant to say there. It'll slow it down because capital letters have longer codes. The RTTY uses variable length codes, just like Morse code does. Like the letter E in Morse code is a single dit. Whereas one of the other letters may be a combination of dits and das, up to 4 of those. And so the common letters, we make them shorter CW characters. We do the same thing here. The E's and the T's and the S's and the common letters are made up with shorter codes so that it will go a little faster. But when we switch over to the alternate character set and get away from the all caps, then it slows things down. Use caps when you need to, but not all the time in RTTY. Back to PSK 31, it's a very narrow band mode. It uses 31.25 hertz. I mean, it is really, really a narrow band mode. The appearance of one or more vertical lines on either side of the received signal is an indication of intermodulation distortion, generally resulting from overmodulation or overdriving the transmitter. What they didn't say in the beginning to introduce that is we're talking about the waterfall display. Most of the programs that we use give you a waterfall display that shows a visual of the signals coming in. You'll see in PSK 31, you'll see usually it's blue unless you change the color scheme. There'll be a blue line that will start from the top of the waterfall and start wiggling its way down. If that little blue line has lines on either side of it and it looks kind of funky and distorted, that means whoever's sending that signal is overdriving their signal. They're overmodulating their signal. It should not normally do that. Also, power to the transmitter is important. We don't want to drive the transmitter so hard we burn it up. That's really what we're saying. We generally set our power between 25 and 50% of its available peak power, and normally that's way more than plenty for anything that we want to do. And as they say, you'd be surprised how a little bit of power can go such a long way. It can be very effective in communications. You don't need 100 watts of power to do that. So you set the power back as well to protect your radio when you're transmitting. The waterfall display we've talked about is that special type of display that shows the digital world. In particular, I'm going to talk about PSK 31. That seems to be what the test is geared toward more than FT8. The waterfall display has three parameters to it. As you look at the display from left to right, it represents the frequency. So if your radio is set to 14.100 or 14.070 for PSK, like we talked about earlier, then on the left end of that display, that waterfall display, you would essentially be at the frequency 14.070. And as you go to the right of that, you would go up to about 3,000 hertz above that, representing audio frequencies above that. So that means that in that 3,000 hertz above the 14.070, you can put a whole bunch of different signals in there all at the same time because they're using such a narrow bandwidth. So you look at the waterfall display, going across the bottom, you see all the different frequencies that are possible. The vertical signal going up and down is time. When a signal comes on the air, it'll start at the top of the waterfall display and go downward. When the signal stops, then the signal will just kind of trail off and it will eventually disappear at the bottom of the waterfall. So it's going from top to bottom, indicating the time that signal's been displayed, basically. And then the intensity or the brightness of the display indicates the signal strength. The brighter it is, the more strength you have. But it's not unusual in those modes to have a very faint signal, a very, very non-distinct signal almost that the radio can still pull out of there and it'll work like a champ. But if you get one that's nice and bright, no doubt you get a 100% copy with no trouble at all. The question they're going to ask is that the standard waterfall display shows frequency on the horizontal axis, that's left to right, intensity by how bright it is by means of the color, and the time is a vertical scrolling line. The time will scroll from top to bottom to show you where that signal is, when it stops and when it starts. Waterfall display can show you a lot of information about what's happening in that 3,000 hertz or so window. And you can change the width of the window if you want to, but usually we leave the window pretty much wide open. Any questions on that so far? There's a picture on the right side there shows a waterfall with just a single display in it. As you can see, going from top to bottom there, you got the blue, which indicates the signal. There's not a lot of strong lines on either side of it, indicating that the sender was overmodulating. So that looks like a good solid signal. Of course, you can always have your radio set to do a monitor tone on it, and you can actually hear what that signal sounds like as it's coming in. And you kind of hear a warbling kind of a tone to it when it's coming in. Okay. So that was just a picture, FYI. Okay, remember the I and the Q. I is the input signal. Q means at least a 90 degrees phase shift. In the digital mode, Q almost always means quadrature, meaning a phase shift or 90 degrees or more, or multiples of 90 degrees, i.e. 90, 180, 270, or 360. QPSK stands for quadrature phase shift, meaning that we are doing a literal phase shift of 90 or more degrees with the signal as it's being applied as well. Normally it'd be, well, as far as I know, it's always a multiple of 90 degrees. That's all. That's kind of the standard. The Q is 90 degrees. That's the two to tie together. QPSK was one of the first digital modes to take full advantage of the IQ type modulation. Symbols of the QPSK 31 signal shifted by 90 degrees in comparison with the more basic and the earlier version of PSK, which came out first, which used the 180-degree phase shift only between the two tones. Because there are more symbols per character with QPSK, it can take more bits, more phase shifts to convey the information. In other words, it has more characters available to it, providing a slight advantage over the regular old PSK 31. It can also, you can program into it if you want to, some error handling, though that's not normally done. Unlike regular PSK 31, it really doesn't care which sidebands you use, but QPSK 31 has to be on upper sideband. It's just that's the software is designed to work that way, and you have to stay on upper sideband with QPS with the Quadrature PSK. Okay, method of using a single sideband transmitter to convert an audio frequency shift signal to a frequency shift keying signal rather, is pretty much universal. But basically, they're saying if it works, don't mess with it. It's the old direct way of doing it. One advantage of the old school FSK allows us to use a very powerful, efficient Class C amplifier. You remember we talked about Class A, B, and B and C amplifiers. Each one of those transmits less, meaning you can drive the whatever the output is, you can drive it a little bit harder because it's not transmitting 100% of the time at full power. So using Class C amplifier lets you basically use more power to get your signal out without distorting the signal. Still in common use by serious RTTY contesters and DXers, of course. The most direct way to create a frequency shift keying signal is to shift the frequency of an oscillator by switching in a small amount of capacitance to change the resonance of the tune circuit that's setting that frequency. So easy way to create FSK, shift the frequency. And the way we shift the frequency is put a small amount of capacitance in there and put it in, take it out to shift it back and forth. PSK is actually a rather unusual code. It's optimized for very narrow bandwidths. As we said, it's 31.25 hertz wide. PSK 31 used a code known as a varicode for its different symbol lengths. Varicode meaning it varies the length of the bits, varies the lengths of the characters with it. The letter E will take fewer characters to send than the letter Z, for example. Varicode. Sound card digital modes apply the audio frequency shift key signal to a properly aligned single sideband transmitter, which then become frequency shift key. The signal consists of two and only two frequencies. That's those frequencies we talked about before, separated by 170 hertz. Intermodulation distortion resulting from overdriving the transmitter will create additional frequencies near the desired ones. In other words, it creates splatter. Just like on a regular sideband, it will splatter the signal on either side of the target frequency. These additional products make the signal difficult or impossible to decode and can also, of course, interfere with other people that are around there if it's severe enough. When using the sound card mode, we need to watch the ALC, the automatic level control. Most all of our newer transceivers have a meter in it, and one of the choices to display on the meter is ALC. Automatic level control is the transmitter trying to optimize the power out of the transceiver. And the digital modes, we're pushing it pretty hard anyway. So we want to cut our power back on the radio far enough that the that the ALC doesn't kick in and try to control it. So you can watch your ALC when there's no signal, and you say, okay, that's like my zero base. And as you turn up your audio signal, your modulation signals, and when that thing starts to move, you back off just a little bit so that you don't get much movement, if any, on the ALC. That way you will not be overdriving the finals, and you'll not be creating intermodulation distortion, and everybody around you will appreciate it, and you'll be able to send and receive much more clearer signals. Everybody's happy about that, of course. Generally keeping the transmitter again down to the 25 to 50% of what it's capable of doing. Okay, any questions so far? I'm just rolling on like a freight train. If you have a question, yell. Okay, hooking up your HF transceiver opens a new world. Yeah, we've said that. Receiving is almost a direct connection to your computer through the sound card. It's not direct, but almost direct. Sending data can require an external modem, such as the PACTOR. PACTOR is a special format, and it does require a special modem to handle its signals. Sending data using an on-off handshake modes like the PACTOR 2 or GTOR, which again are just two of the modes of sending it. The PACTOR does require a special modem, as we said. Let you transmit and receive for a duty cycle of perhaps 50%. Don't want to push it too hard. Other modes like PSK31, MFSK16, transmitting a constant key down data stream. Your duty cycle on those modes is 100%. On the PACTOR, it's not. You can use the Class C amplifier because it's not transmitting at a duty cycle of 100%. The heat sinks on the back of your receiver get roasty toasty. I kind of like that term, roasty toasty. So they're saying then can either cut the power back a little bit, cut the modulation back along with it, or put a big fan on the back and keep it cool, but you still risk blowing up the the final output transistors in your transmitter. No, don't want to exceed the transmitter's average output power, which can blow up those transistors. Okay. Big boats go slow out of the harbor so they don't create large wakes for the other smaller boats. Same thing with our digital modes. We don't send fast, but if we send fast, we have to have a whole lot more bandwidth. It affects a lot more people that way. Faster sending, speed, faster. Let's see. Higher bands will be necessary for fasting sending speeds and wider bandwidth. At the lower frequencies, we don't have enough bandwidth on those lower frequencies to support high data rates. That's why we get into serious high data rates. We'll normally always find those at VHF, UHF, or 70 centimeter or microwave frequencies. We get way up there in the high speed frequencies when we get into serious data transfers. Radio teletype emissions below 28 megahertz, below the 10-meter band, are limited to 300 baud, which is relatively slow. This slow rate is required to minimize the bandwidth allocation. So that keeps our bandwidth down. That's the reason we're limited to that. The exception being 1200 baud here on 10 meters. You can run up to 1200 baud, which is 4 times faster. But and of course, it's perfectly okay to do that. And the reason they're governing that is so that we don't do the splatter and try to take up or hog up too much of the bandwidth when everybody's trying to share the band. When we send the message will start with a header, which has some routing, address information, handling information, start, stop bits, etc., things that tell the receiver this is the beginning of a message. So within the header, they have the routing addresses, handling information. For digipeater, is just some sort of a digital receiver, whatever that is. It's your receiver receiving digital, or it can be a dedicated radio doing that, whatever it happens to be. Would direct your packet to over a specific route, even coast to coast or worldwide if we're into a net doing that sort of thing. If you're into APRS, which is what this is leading up to, APRS stands for Automatic Position Reporting System, unless you read newer literature in which it means Automatic Packet Reporting System. The name changed there somewhere along the way. APRS is a function built into a lot of our radios. It allows our radio to report our position in latitude and longitude to a digipeater, and our club does have a digipeater, although it's down right now. Our digipeater was co-located with our main repeater on UHF and Wires X. It was co-located with that. And of course, Melissa is overhauling the water tower. We had to take everything out. So our digipeater is down. But if you were running nearby and you were doing APRS, you would see here a little burst of data go out. It would go out to our digipeater. Our digipeater would pick it up and retransmit it to another unit somewhere. And eventually it would go into a central database. There's a thing called APRS FI. It's actually a site in Finland that tracks all these things. You can go there and you can pull people's call sign up and see where somebody is literally on a map with APRS. So APRS is wonderful. It's used a lot when we're doing parades or we're doing public service events or bicycle rides or things like that. So anyway, the header is the key to that, to the question that's going to be asked. The header contains routing addresses and handling information to get the signal where it's supposed to go. The control operator Must be physically present at one end of the radio circuit or link, and that's normally true. If two of us are sitting together by my radio, and I'm on the extra band, and you don't have an extra license, then I'm the control operator. You can talk on it, and if somebody challenges us, I go on. I say, "Hey, it's okay. I'm the control operator here." We do somewhat the same thing with the digital, except it's not as critical because the text can do most all of this that we're talking about on some of those frequencies. So, at any rate, we still have to control what we do. It still has to remain under somebody's control. So, in other words, normally automatically controlled relay stations can't talk to one another directly. Exceptions to this: the 6 meter and some of the shorter wavelengths, that is in the 2 meter, 70 centimeter, the really high frequencies. A few specially designated slots on the HF band. Again, that's the 60 meter band. I said 6 meter earlier, excuse me, 60 meter here. All cases, however, there must be a control operator at some point in the total radio length. Now, there's special frequencies that are set aside for controlled frequencies, and we can use that control frequency to control a remote transmitter. And so when we talk about remote control, that's one of the ways we can do it. But there has to be somebody somewhere that's the control operator, either controlling it by sitting at a radio that is sending remote control instructions and monitoring, or has to physically be present with one of the radios as it's transmitting. At some point, though, there has to be a control operator there. Okay, we just said that. Sometimes it can be a little bit tricky to determine. In the case of Echolink or IRLP, IRLP is the Internet Relay Linking Project, somewhat similar to Echolink. The control operator may be located clear across the country. Of course, we have some people who check in on Sunday night from Georgia pretty regularly. When that person from Georgia checks in, he is actually his own control operator. He is the control operator for that signal. Even though he's coming through and activating our repeater, he's still his own control operator. So we have to have a control operator, whether it's Echolink, IRLP, or whoever it happens to be. Has to be a control operator. Encrypted radio signals are prohibited, period. That's just part of who we are. Use of encryption is contrary to the very nature of amateur radio, which from the very beginning was to be fully open. To avoid falling under the no encryption rules, hams using new digital modes. This is if you invent a new digital mode you want to use, you have to publicly document the technical characteristics of that protocol so that anybody has access to it and they can use your protocol if they choose to do so, and they can understand what you're doing in order to receive that new mode. So the key to it is, if there's a new mode comes out, it must be publicly documented for all to see. The technical characteristics must be available to anybody who wants it. RCA phono jack. Does anybody know what that is? Yeah, that's one of those little audio jacks, basically. Back in the old days when we had component stereos, you had a turntable with a cable that plugged into the back of an amplifier. Usually those plugs were RCA plugs, as they were called. They're low-frequency audio jacks. A lot of the backs of our radios will have that RCA jack on the back of it, used for amplifier keying. It's basically a control line to key your power amplifier on and off. And yet some will use an external low frequency receive long wire antenna that will go into a signal like that if you have a special long wire receiving antenna, sometimes for DC signal connections to the radio for a controlled signal, or something that will tell an external device something it needs to know about your radio. The key to it is RTFM, and you know what RTFM means, right? Read the fine manual, and we're going to drop it at that. WinLink, automatic message network using VHF and UHF, and take that with a grain of salt. There's a question to this effect, and the answer they're looking for is using VHF and UHF. However, we do use WinLink on the HF bands as well. Very popular on the HF bands, but for this particular question, this is kind of a gotcha. Watch out for VHF and UHF as the answer. WinLink itself does not define the actual protocol. WinLink is really a system, a gateway system that processes the data, but it doesn't define what protocol you're going to actually use. Gone over a lot of changes. It uses a variable length character that we send. Most common protocol running underneath the WinLink system. So the variable is the protocol that is most common. WinLink remote messaging server is the gateway. So when we send out something on WinLink, it would go to the messaging server. The messaging server then would hook to the internet and take it wherever it needs to go in most cases. WinLink is one of the most popular automatic message relay modes. Vera is a specific digital protocol used by WinLink, providing transparent, familiar email interface. Most common use for WinLink is to send email, by the way. If you've never got into WinLink, you have to register with WinLink, and you actually get a WinLink email address that's registered with their servers. If you have that address, I can go to my computer in Windows, just regular using Microsoft Outlook, regular old Windows messaging, and I can actually send you a message that would go through the WinLink server and be stored on that server, waiting for you to come pick it up when you log in the next time using WinLink. So it's a pretty robust system. Works very, very well. Used a lot for emergency communications. I'd say primarily even used for emergency communications. The gateway is an interface between the different systems, such as between the internet and amateur radio. WinLink is one of the most popular gateway technologies, combining email and, in most cases, HF radio. This is where what I said earlier. WinLink is used on HF all the time. Why they put that question in there about VHF and UHF, I'm not really sure what their intent was. But to access one of the gateways from an HF station, you would transmit a connect command. So you're using software, using the WinLink software, and you would formulate a command that says, go to my radio, have my radio on this frequency, whatever that listening station's frequency is, and transmit a command, digital command that says, hey, I'm out here. Can you hear me? That's the essence of it. And then the link that's out there, the gateway station that's out there would respond with an acknowledge saying, yes, I hear you. Send me the first piece. And then your radio would send the next one. And then they sit there and go back and forth, handshaking as they go. Did you get it? Yes, I did. Then send the next one. No, I didn't. Resend the previous one. So they go back and forth talking to each other to make it pretty much error-free, unless it's just the conditions are just so bad you can't communicate at all. Once you're connected, the link is transparent from your terminal. Looks just like you're on an internet email client. Works just like regular email, basically, once you're connected. PACTOR. A number of other digital modes operate in a connected mode, meaning they connect one station to another. They're limited to just those two stations. The connected mode only works between the two stations that are talking to each other. Now, you can hear the conversation, but they don't have any means of having a third party come in and talk for a three-way conversation. So the key being these particular methods like PACTOR. The downside is the connected mode only works between two stations at a time. No rag chewing, no general conversations. It's two stations communicating with each other. And normally they're sending the acknowledged request back and forth. That's the reason it's, in essence, a closed conversation between those two stations. Most HF digital modes are fairly robust, generally include some kind of error correction, not always, but in most cases. And of course, no system's perfect. HF itself, of course, signals can fade. We can have interference. There's all kinds of things that get into the mix of what we're trying to do. An HF communications link undergoing interference can suffer symptoms ranging from, and this is one of those questions that the answer is all of the above. And the answers are, you can have long pauses in the transmission, frequent message retries and timeouts, and a connection failure. So the two radios are going back and forth trying to communicate with each other. And if it gets to the point where they can't, then the receiving end of it will basically just say, I quit, and stop listening to you, and just break the connection from you. Sometimes it's good to know when to quit. Yeah, it's true. PACTOR and WinMore, both common protocols to use with WinLink again. We'll make numerous attempts to set up the connection, maintain the link, keep it going. But when they can't do it, it will drop the connection. Usually there's a predetermined number of tries that it will go back and forth. I don't know what that number is, but it's a predetermined number, and then it'll drop the connection if it just can't communicate after that. It'll quit listening for you anymore. Okay, transmission message is sent in short bursts. or short segments, if you want to call them that, allowing the receiving station to quickly transmit and acknowledge for a perfect copy, or a not acknowledge if it was not a perfect copy. NAK, then we usually call this ACK-NAK, just to give it something easy to say. If it sends back a NAK request, it's telling the sender, send it again because I didn't get something that I didn't copy correctly. And so that the sender, if that's you, would send it again. And then if you get back an acknowledge, yes, I got it, then you would send the next packet. And it would go back and forth like that as long as the two can communicate. Forward error correction, usually called FEC, is achieved by doubling the data in the packet, basically putting the data in the packet twice. So the receiver will look at the first set of data. If it's a little garbled, it'll look at the second set of data, see if it can construct a good packet between those two sets that's in one packet. And if it can, it's good. If it can't, then it'll send back a not acknowledged and ask you to send it again. Laws of physics, no free lunch. And I guess that's really true, isn't it? We try to extract those little signals out of there that we can't even hear. They're below the noise floor, perhaps. Extremely weak signal methods, either of digital, such as FT8, and that's one of the keys that they mentioned. A weak signal method today is FT8, or analog, such as the lock-in amplifier, need to do their magic. Sometimes a lot of it. Data speeds are low. Bandwidth is very low, of course, which is good. It's the price we pay to be able to communicate. So the key to that whole thing is they're going to say something to the effect, for extremely weak signals, use FT8. We sing the praises of the I/Q modulation, the input/quadrature modulation, and how we can determine the degree of phase shifting on an IQ demodulator. FT8 takes a different approach. They use an 8-tone frequency shift keying scheme. The frequency shifting is slow enough you can actually hear it. You get a little bit of a warble to it when it's being sent. Been described by some hams as a space alien orchestra tuning up as you hear all these different tones going back and forth for FT8. FT8 is a structured digital mode. It requires very precise timing. Normally, you have to be within plus or minus 1 second of universal coordinated time because it is timing sensitive specifically. It knows that on the second mark, certain things are supposed to happen. At the 2-second mark, some more things are supposed to happen. So it has timing in order to make it all work together. You don't have to have an atomic clock to do that. Generally, you can set your computer using WWV or WWV Hawaii. One thing goes, it tells you the exact minute and second, and it goes tick on the minute, and you set your computer that. That normally would be enough. Most of us, however, would use an automatic service from Windows or whatever system we're using that will automatically sync our computer's clock with universal coordinated time, so we don't have to worry about it. That always keeps us in perfect timing that way. FT8, for a while, drives home the point about the signal-to-noise ratio. Far more important than merely the signal strength. As we said, with FT8, the signal can actually be so low you can't hear it. It can actually be below the noise floor. Signal-to-noise needs to be qualified by the bandwidth. In this case, the answer is FT8 is 2.5 kilohertz, about the same as a typical sideband signal. Excuse me, and that's read out in dB. 3 dB is 2.5 kilohertz in FT8, if you could just kind of put those two things together in your mind. Working DX on HF, standard practice to operate split. If we're using voice, we would transmit on one frequency, receive on another. That helps to cut down on some of the traffic jams we get into for that. But on FT8, we don't do that. We don't have that luxury. Since FT8 is using timing so critically, we pick another frequency, which is right close. I mean, it's just a few cycles off. Pick another frequency, and then pick a different time slot than what the sender is using, and the two will blend together, and it works really well. So allowing the X signals to stations to be heard outside the inevitable responding pilot. So with where that's on HF. On FT8, we find a clear frequency, we transmit on the opposite time slot. That's the answer. This thing right, that last sentence is the answer of the question they're looking for. FT8 operations on the traditional non-work bands takes about 70 to 75 kilohertz from the bottom of the band. 20 meters, FT8 place that you'll see most of the activities between 14.074. You remember 14.070 was PSK. And here we run between 14.074 and 14.077 for FT8. Spread spectrum. Another thing we've not talked about. Spread spectrum is where we will transmit on different frequencies in a certain order. We'll transmit a little bit on frequency A, transmit a little bit on frequency B, on frequency C, or however many we're using, sometimes called frequency hopping. We spread it out. Allows two or more conversations to occupy the same bandwidth because we do time slicing with that, and we share that time together. The technique has to be used with caution in a few places on the amateur bands where it's allowed, particularly in this spectrum shared with other non-amateur services. Particularly what we're talking about here is 2.4 gigahertz. If you remember, most all of our Wi-Fi routers that we have in our homes operate at 2.4 gigahertz or 5 gigahertz, and those are shared frequencies. We as amateurs can transmit and receive on those frequencies. If we want to set up a network, a wireless network, we're authorized to do that and share those frequencies, use those frequencies using spread spectrum. But our power limit is 10 watts peak envelope power at the transmitter output from our router. So we can have more power than your home router has, which is normally limited to 100 milliwatts. So we can go to 10 watts with this, and we can be very, very effective with that at the 2.4 gigahertz frequency range. Okay, key part to this is, in no part of the 2.4 gigahertz band can amateurs communicate directly with unlicensed stations, period. And of course, that's kind of throughout all. We're not to communicate with unlicensed stations, period, anyway, except in times of dire emergency to save life, limb, or property. 2.4 gigahertz is the shared band that we use for spread spectrum. We do our networking through that. There's a couple of different network formats we'll talk about here in just a moment that uses 2.4 gigahertz. Mesh networks was one of those techniques. Have multiple paths between two nodes. The great part about a mesh network is that if one node goes down someplace, your signal going through can go to a different node and still get to where it needs to go. Just reroute around the one that's down. So they have multiple paths to get to wherever things need to go. Doesn't matter if it's a microwave network or in the UHF frequencies or where it happens to be. It just figures it out and it gets it there for us. A couple of the other common modes are the star mode. Star meaning you have a central hub and then spokes that stick out like from a wheel for the different nodes. And the daisy chain means we have one connected to the next, to the next, to the next in series. That you might use the daisy chain if you were trying to cover a really long distance. And the star mode or the multiple path or mesh mode would not work for you. Another term you'll see is ARDN, Amateur Radio Emergency Data Network, and there's an ARDN network in our area, and it does use the 2.4 gigahertz for that. You can set up an ad hoc network on the fly if you needed to in an emergency situation. Most of us would not do that, but we could. It uses commercial off-the-shelf equipment, routers and such. We just put different software in it. At one time, there was an old Linksys router that every amateur wanted a couple of because you could reprogram it with special software and use it just for this. And that was early on enough that not a lot of the manufacturers would let you reprogram their routers. But at any rate, uses regular off-the-shelf stuff, but we download some special software to use it for our purposes. The number of gains and losses associated with achieving a given signal strength at a receiver at some distance from the transmitter is called the link budget. In other words, we take all the gains out of the transmitter, including the gain of the transmitter itself, the gain at the antenna, and then the receiver's in, if he has loss or gain, if he's got a gain antenna or a loss antenna, loss in the coax and all that. And we come up with a number for that, and we call that the link budget. I'm not sure what we use that for, quite frankly, but it's there, and it's one of those questions that's there. The key to it is it's the sum of all the things attenuating or affecting the signal between the transmitter and your receiver. It's called the link budget. Okay, let's see here. The link margin is related to the link budget. What we would like to have and what we see is the difference between the two. That's called the link margin. How much margin do we have in order to be able to still receive this particular signal? Difference between the two is the link margin. That's the key to that question. Okay, in addition to all the digital things we talked about for digital communications, where you use the keyboard, we type the stuff in, go back and forth. There are also voice digital out there. Most popular, DMR, digital mobile radio, which was started by Motorola years ago and it adapted to ham radio. D-Star, which is hosted primarily through ICOM. It's proprietary to ICOM in practical life. And then System Fusion, which is Yaesu, and it's proprietary to the Yaesu world. Of course, then Yaesu System Fusion is the repeater that we have, which is currently out of service in Melissa, waiting for the water tower to be taken care of. So a lot of different things out there we can do with the digital world, digital data, or digital voice. And then let's get on the questions and see if we can get through these. And can we cover these questions? Whatever 40 questions in 8 minutes? Probably not. Here we go. Baudot code, you remember, is a 5-bit code with a start and a stop bit. Answer C. And I'm going to go kind of quick on this. If you have a question, you want me to back up or slow down, just say, hey, wait, I can back it up or I can slow down or we can talk about it if we need to. Most common frequency shift for RTTY is 170 between the two frequencies that it uses. Okay, they're identified by their digital signals, but we don't call them highs and lows or on and off or 1 and 0. And most digital world would call it, how to have us do, we call it mark and space. Mark is a 1, space is a 0. What mode do we use with RTTY? We always use lower sideband, unless the other end's screwed up and they're transmitting on upper sideband inadvertently, in which case we flip to upper sideband, then we could receive the signal. But normally it's going to be lower sideband. What could be wrong if you can't decode the RTTY signal or some other signal, even though everything looks right? The mark and space frequencies may be reversed. They may have their software screwed up, so it's sending 1s and 0s backward. You could have selected the wrong baud rate or the wrong speed of the transmission and receive. You might be listening on the wrong sideband, and that's one of those. All of those are correct. It could be either one of those. Standard sideband for JT65, JT9, and most of the other things that are out there. Unlike RTTY, which is lower, we use upper for everything else, including FT8. Advantage of IQ modulation, that's the input and quadrature input signals. We can create anything we want to. Using the phase shifts and other things, we can just about create any kind of processing we want with that thing. It's software definable. We can do most anything with it we want to at very, very low cost. What segment of the 20-meter band are most PSK operations generally found? You might remember that frequency. 14.070. Watch out for that 14.100, which is tempting, but that's the CW. Okay, it's 14.070 and to 14.100. Which of the following statements is true for PSK 31? Anybody want to guess that one?
B.
You got it. Uppercase, use varicode signals. What is indicated on the waterfall display by one or more vertical lines on either side of the data mode? Means we're pushing, the sender is pushing his radio too hard.
Mod.
He's overmodding. He's pushing it too hard, making it overmodulate. Oops, wrong button. Which describes the waterfall display, and this is one I have to read these to get it. It just doesn't jump out to me. But you'll remember we said that along the horizontal edge we have the frequency displayed, starting out at whatever the frequency we're targeting, say 14.100, and then going to the right of that we go up about 3,000 hertz. So frequency is in the horizontal. The signal strength, how strong the signal is indicated by the intensity of what we see, how bright the signal is. And then time is indicated vertically up and down as we see the signal come down through the waterfall display. We can track the signal in time. So the frequency is horizontal, signal strength is intensity, and time is vertical. Answer is C. I hope that helps. What is QPSK? Look for something that says 90 degrees. That's the quick and easy way to do that. Use 0, 90, 180, or 270 degree phase shift. Following a characteristic of QPSK, it has to be on the correct sideband. Its encoding provides a wee bit of error correction. Its bandwidth is about the same as regular old binary PSK, regular PSK 31, which is 31.25 hertz. One of those, all are correct. Direct binary FSK modulation is generated by changing the oscillator's frequency directly with a digital control signal, or putting a little capacitance in there with it, so we shift the frequency ever so slightly. In this case, we're looking for the digital control signal because we are talking digital. What type of code is used for sending characters in PSK 31? Remember, that was the vary code with a variable length characters in order that the shorter characters would send faster. Why should the automatic level control system be inactive when transmitting these digital signals? If the ALC is showing a whole lot of activity, if it's trying to control your radio, then it's may cause your transmitter to overheat, that's for sure. It can also indicate that it's jacked your transmitter up, so you're distorting your signal. Could even invert the modulation of the mode, mess it up so that I just messed up. I thought it was all answered. My apologies, back up. ALC action distorts the signal. Never mind. I was thinking something totally different. Don't listen to everything I say every time. Okay. Oh boy, that's embarrassing. Why is it important to know the duty cycle of the mode you're using when you're transmitting? We don't want to break the radio, do we?
B.
Do you agree? B. Yep. Don't want to exceed our transmitter's rating and blow it up. Relationship between transmitted symbol rate and bandwidth. If we transmit lots more, it takes a lot more bandwidth. So bandwidth, let's see, a higher symbol requires a wider bandwidth. What is the maximum symbol rate permitted for a RIDI? Below 28? It's slow.
300.
300 baud. It's slower than syrup on a cold day. But if we go 10 meter or above, we get to go all the way up to 1200, 4 times as fast. And that's because we're dealing with a higher frequency that can handle that extra data. What part of a packet radio frame contains the routing and information handling that goes through? That's going to be the header, the first part of it. The packet is the whole container for all the data that's going to be transmitted at one time. The beginning of the packet will be the header, which gives the routing and handling information, telling the receiver what to do with the data and how to handle it. What bands may be automatically controlled? On what bands may automatically control stations transmitting RIDI or data emissions communicate with other automatically controlled digital stations? Excuse me, sorry.
D.
Oops. No, not quite. And this has to do with somewhat with the frequencies. Anywhere where the 6 meter or shorter wavelength bands, limited segments of the HF bands, that's the 60 meter band that we're talking about there specifically. But at any rate, when we get in the higher frequencies, we're allowed a lot more latitude in the control. That's the objective behind that. What is required to conduct communications with a digital station operating under automatic control outside the automatic control band segments? Whoa.
A.
That's it. Somebody's got to control it. Normally, it's the person initiating the call. What must be done before using a new digital protocol? So you invent a new way of doing it before you can use it. What do you have to do?
Publicly document.
Publicly documented so anybody else can use it if they want to. No secrets. Which connector is used to pass a DC signal or low frequency control signal out to our amplifier?
C.
LRCA jack. WinLink, an amateur radio wireless network to send and receive on the internet. And that's basically what it's doing. Also a form of packet radio because it's sending packets back and forth. A wireless network capable of VHF and HF band. I think you remember I had that one question that talked about VHF and UHF, but it can do both. Okay. Another name for a WinLink remote message server is the
Gateway.
gateway. Avara is one of the protocols that WinLink uses to vary the character lengths. Which is the following way to establish contact with a digital messaging system? Gateway, how do you contact that gateway and let it know you want to talk to it? You transmit a connect message. Say, I want to connect to you. How do you join a contact between two stations using the PACTOR? You remember PACTOR is between two stations only. So what do we do in that case? It's not possible. Can't do that. C. What symptoms may result from other signals interfering with the PACTOR or the VARA communications? If it's trying to go back and forth, and when it has a problem, it'll try to do a retry or a timeout. Be long pauses as it does all this back and forth. It may not be able to maintain or establish the connection. So this is another one of those, all of the above. What action results from a failure to exchange information due to excessive transmission attempts when the AR using ARQ mode? ARQ is automatic automatic receive request. Automatic receive in the queue out of request, or ARQ, or automatic receive request. Okay, I forgot what the question was now. What results when we have excessive transmission attempts? Oh, okay. B, exactly. If it just can't go back and forth, it can't do it, it can't respond, and it'll drop the connection. In the ARQ mode, what's meant by a not acknowledged, or NAK? Means I didn't receive it. You need to send it to me again. Forward error correction allows the receiver to correct data errors, generally by putting redundant information in the packet. Which of the following narrowband digital modes can receive signals with very low signal to noise ratio? Remember we talked about that? FT8. We're getting there, gang. We're going to make it. Hang with me. FT8 uses 8 tones. What's required when using FT8? Doesn't have to have anything special in hardware. Don't have to do any weird thing with antennas. You got to have good timing. You got to have accurate timing. When an FT8 reports a +3, it means it's 3 dB over 2.5 kilohertz bandwidth signal to noise ratio. And that's one of those canned answers that it's best just to memorize it and don't worry about it. Which of the following is good practice choosing a transmitting frequency to answer a station calling CQ using FT8? Well, we don't want to transmit on top of it, so we need to get a clear frequency, and then we're going to use an alternate time slot from what he's using. That way, the other side can hear us. So we get a frequency using an alternate time slot so that he can hear us. Common location for FT8, where's FT8 usually found?
C, Charlie.
C, exactly. 074 to 077 on 20 meters. Maximum PEP output for spread spectrum transmissions. That's our Wi-Fi world, our 2.4 gigahertz. Max power is
10 watts.
10 watts. No. Of course, at that frequency, 10 watts is a lot of power. What part of the 2.4 gigahertz band can an amateur station communicate with a non-licensed Wi-Fi station?
None.
None. What band amateurs share channels with for the unlicensed Wi-Fi service?
Charlie.
2.4 gigahertz. Mesh network, microwave networks. Remember, the deal on the mesh network is there are multiple paths to the same destination. So if one node fails, the packet can route around it and still get there on an alternate node. I lost the mouse. There it is. We're getting there. Primary purpose of Arden mesh network. Key to that was going to be emergency and community. High-speed data services in an emergency or for community events like parades and bike rides and such things. A link budget. The sum of the transmit power and antenna gain minus system losses seen at the receiver. Everything that affects the signal from the transmitter to the receiver is the link budget. The link margin is the difference between receive power level at the minimum required signal level at the input to the receiver, which is double talk. But that's the answer. What can I say? Which services provide digital voice modes? DMR, digital mobile radio, D-Star, which is ICOM, and System Fusion, which is Yaesu. Guess what's next? How's that? Okay.
Right. Well
we
done.
did it. We did it. 8:07. Hey, we're doing good. Woo. That was rolling fast, though. Hopefully that helped. Hopefully it does two things. One, it helps you pass the test. But two, if you do get into the digital operating modes, if you've not done much of that before, you'll have a leg up on it when you go into it and you read the terms and you kind of have a heads up and you know what they're talking about. And digital is a lot of fun. It really is. It's a lot of fun. A lot of people don't like it. A lot of people don't like FT8 because you don't carry on a conversation with FT8. You just say, I'm here, I receive you this strong. And they come back and say, I'm over here and I receive you this strong. Goodbye. And you go to the next one. You know, it's if you like that, that's fine. And some people do. But any questions, any discussion, anything about anything? Ready to go take the test Sunday?
I hope so.
Maybe. Maybe. Well, if you do, I certainly hope you do. Guys, this was our last session, and I appreciate you being with me. I know a couple of you have used the online on YouTube sessions to review, and of course, that's what they're there for. Glad that you do this, and this will be on there as well after tonight. And if there's anything I can do for you, you have my email address, my phone number. Please contact me. Or if there's a question that you're not clear about or you want some clarification, help, whatever, by all means, contact me and let me know, and I'll be happy to do anything for you that I can. Also, should be getting the manuals for extra in here before long, and we'll see about scheduling something for that here in the not that distant future. So with that, I'm going to go ahead and stop the recording. Thank you so much for attending, guys.